Well, thanks, Vento. You've done all the hard work. And
Can't see.
oh. Yep. I'm Peter Jarvis, one of the members of the local biomathematics phylogenetics group, and welcome to everyone here and the distant people. This is a good session, student talks, but it seems to really be focused on a kind of model investigation. So I'm interested to hear the presentation, starting with Ahmed Ashar from Aalto University. That's got to be Finland, and it says it on your on your overhead when you can share it.
Yeah. Okay. Can I start now? Okay.
Yes, please do.
Let me share my screen. Okay. So I hope you can see my screen now. So thanks for the opportunity you gave me to be able to give a talk in this wonderful occasion. So I'm Muhammad Ardiansha. So I'm a third semester PhD student at Aalto University, Finland. And today I'm going to talk about our joint work with Kai Kubias and Dimitra Costa, and it's about the model embeddability in symmetric group-based model. So let's get started. And in the embedding problem, if you're given a stochastic matrix or Markov matrix, then you want to know whether your stochastic metric is a metric exponential of some rate matrix. And if your favorite stochastic matrix can be expressed as a matrix exponential of some rate matrix, let's say P is equal to exponential of some rate matrix Q, then we say that the stochastic matrix P is embeddable. And just to remind you what an exponential of a matrix is, it's just defined as this following series of matrix. And then some result for the embeddability criteria for n at most 4. So the dimension of the matrix is at most 4. It's completely solved. For example, here you can see some earlier result for n equals 2, 3, and 4. For n equals 2, for example, you can see that this embeddability criteria, the necessary and the sufficient condition is given by having the determinant is positive and at most 1, or having a trace of this metric of the Markov matrix is greater than 1. And for n at least 5, there are some partial results. For example, in this paper by Michael Bake and Jeremy Sumner, they investigated this equal input matrix and also circulant matrices. So yeah, that's a bit of background. And now in this talk, I'm going to focus on the embedding problem that comes from phylogenetic models. And in particular, I'm going to talk about a symmetric group-based model. And in phylogenetic, there are some approaches used in modeling the evolution. The first approach is to use this continuous time substitution model. And in this model, we assume that the mutation matrices are a result of a continuous time Markov processes operating for some non-negative period of time. So so for each branch of this phylogenetic tree, you have a Markov matrix PE, then it's of the form of exponential of some rate matrix QE times TE, which is the elapsed time. And the other model, what is called algebraic model, and in this model, we takes into account only so you are given conditional probabilities between the original and the final sequences, DNA sequences, without caring much about the rates of mutation. And so this embedding problem really connects these two approaches from algebraic model and continuous time substitution model. And as we know, usually the structure imposed in the model is most of the time motivated by these biological or biochemical properties. Just to remind you, this there are three example of most widely used group-based model. They are this Jukes-Cantor, Kimura 2 parameter, and Kimura 3 parameter. And here the symmetry that is imposed in the model is motivated by these biological properties of these nucleotides A, C, G, and T and their interaction. So we already know what the classical embedding problem is, but here we will focus on what's so-called the M-model embeddability. That is when we impose the additional assumption that the rate matrix Q should also follow the corresponding model condition. So for example, if you start with a Jukes-Cantor Markov matrix, then you want to find a rate matrix that is also have the symmetry that is given in the Jukes-Cantor model. So let's get started with the group-based model. So you start with a finite additive abelian group G and a set of labels L. And here I say labeling function is just basically any function on the group G to the set of labels. And then based on this labeling function, we can define what is GL rate matrix. So it's the rate matrix where the entries of this rate matrix are given by the following. So the GH entries of this rate matrix is given by this value of some factor in RG, and this factor has to sum up to 0, and then for the uh, for non-zero G, the value of this factor psi is non-negative. And also we have the additional requirement that the value of this function psi at two element G and H, they are equal whenever the label of G and H are equal. Okay. In the literature, most of so the group-based model considered in the literature are time reversible. So here, that's why we take into account the symmetricity of the matrix. So if you have your rate matrix is symmetric, then it means that your factor psi here satisfy that psi of G is equal to psi of minus G for every element G of the group. Then if you take the exponential of this matrix, then the entries of the resulting Markov matrix should be, so the GH entries of this matrix is given by the value of some probability factor F at the point H minus G. Since you have your starting rate matrix is symmetric, then your Markov matrix is also symmetric, which is obvious. Then furthermore, if you add additional requirement that this probability factor F satisfies the property that the value of this probability factor F at two element G and H are equal whenever the label of G and H are equal, then we say this Markov matrix is a GL Markov matrix. So it's determined by the labeling function L. One observation is that if you start with a GL rate matrix, then the exponential of this rate matrix is not necessarily a GL Markov matrix. So it could be that the labeling function of the Markov matrix is different. Here is an example. So you consider a group with 7 elements is 7, and then you consider a labeling function where you set the label of 1, 2, 5, and 6 to be equal, and then the label of 3 and 4 to be equal, but the label of 3 and 4 it's different from the first label. And then, for example, you consider the following rate matrix Q uh, that is determined by this labeling function. And if you compute the exponential of this rate matrix, then you see that here it's not GL rate matrix because the label of the element 1 and 2 are different. So we label each row and column here by the element of the group. So here's because we have the element of the group is 0, 1, 2 up to 6, then we will label the row and the column by 0, 1, 2 up to 6. Another example, if we consider group-based model on Z3, where the label of 1 and 2 are equal, then okay, we suppose have a Markov matrix P and also a rate matrix Q, and they are related by this exponential, and so we know that this P is a Z3L embeddable. But if you replace this constant 0.25 by some other number that is bigger than 1/3, but less than or equal to 1/2, then P is no longer Z3L embeddable. So here the one example of model embeddability. So if since we have a group-based model, there is a very useful method to that applies to group-based model. So we can use a Fourier transform. It is basically an invertible transformation between collection of H parameters and the corresponding sat pattern frequency factor for a given tree. So Fourier transform often used in simplifying. So in when you compute the joint probability distribution, you have this polynomial parameterization of the entries, and then using Fourier transform, you can simplify this polynomial parameterization to monomial parameterization, which is a nice description of the model. And since it's invertible, so we can represent it in the terms of matrix K here. K is the discrete Fourier transformation matrix. And then we say a labeling L. Oh, okay. I need to mention this factor XL. So XL is a column factor that basically captures the labeling of the group element. And then we say a labeling L, a G compatible, if for every two element with the same label, when we compute the multiplication K times label factor XL and K inverse time this label factor L, then when we see the G and H component of the resulting factor, they also have to be equal. So that's what a compatible G compatible labeling is. So for example, for Kimura tree and Kimura two parameter model, they are a group-based model associated to this Z2 times C2, which is a group with 4 elements. And then we have the corresponding discrete Fourier matrix as the following, which is the Kronecker product of two Hadamard matrix. And then you can see here, Kimura three parameter model, it's a G compatible, and Kimura two parameter model is also G compatible. So here is the main theorem for this talk. So if you have a symmetric G compatible labeling function, then GL Markov matrix is GL embeddable, so model embeddable if and only if the set of eigenvalues satisfies the following semi-algebraic description. So one of the eigenvalue of course has to be 1, and then eigenvalues has to be positive, and there is this some other criteria that has to be satisfied by this eigenvalue. So, okay, I think I will skip this. Okay, for the Kimura tree parameter model, for example, the eigenvalue is given by these following 4 numbers. And using this criteria, we say that a K3P Markov matrix is K3P embeddable if and only if it satisfies the following equation and inequalities. So this is basically the criteria that appears earlier in the paper by Jordi Roca and Jesus Fernandez. And I would like to mention here that the classical embedding versus the model embeddability. So for the Kimura tree parameter embeddability of Markov matrix with no repeated eigenvalue, this the notion of embeddability and the model embeddability, it's equivalent. Similar thing also happens for the Jukes-Cantor model, but but it's not true for the Kimura two-parameter Markov models. So what can you do if you have this characterization, and then so you can compute, like for example, compute the volume of the model embeddable Markov matrix and compare it within the volume of the whole space of Markov matrices in the model. So for example, for GC model, that you can see like 75% of GC Markov matrices are GC embeddable. Here, I'll also some example that we have in our paper for Hachimoji three-parameter model. So basically, that's a DNA model for 8 states. And here you can see that the yellow one, which is the set of all Markov matrices in the model, is given by this polytope, and then the orange is the set of a Markov matrix with positive eigenvalue, which is again a polytope, but the set of embeddable Markov matrices here is semi-algebraic set. And one last thing, one last thing here. So if you have your GL Markov matrix is GL embeddable, then there exists unique GL rate matrix that satisfy this P equals to E to the Q, and it's given by the principal logarithm of P. And this set of GL embeddable matrices for a symmetric group-based model, it's basically an intersection of closed subset of Rn and one of the connected component of the complement of this determinant, the vanishing of this determinant of stochastic matrix, because we have that this eigenvalue of this matrix should be positive. So in summary, this model embeddability is they can be characterized by this algebraic condition on the eigenvalues. And then here I would say that this model embeddability is a different refined notion of this classical embeddability problem. So that's it from me, and here I will leave you with some references. Thank you.
Thank you very much. We've got time for one quick question, I think. Jeremy?
So Jeremy Sumner here. Thanks for the talk, Mohammed. I guess an annoying question perhaps for you is what about getting rid of this condition about the symmetric group-based models? So in your result, can you just go back to the main theorem? I mean, how important is that to the main theorem?
Yeah.
Yeah, so what's the difficulty if you try to remove symmetric from this statement?
Oh, okay. So the symmetricity here, so basically plays a role in, if you have a symmetric matrix, then your eigenvalue will be real. And yeah, basically when we rely on those facts. So that's why we have this symmetric assumption.
And you see no easy path if you move into where you have complex eigenvalues?
I simply don't know. Yeah, probably there are more needs to be done for that case. I don't know.
Thanks, John. Well, let's thank Mohammed again. And we'll move on. The next speaker is Clausius Manuel from Vienna. And you're going to talk about matrix exponentials again, matrix exponentials and maximum likelihood for phylogenetic inference. Are you there, Manuel? Cassius, sorry.
Mm-hmm. Okay.
Is there? You can share your screen.
Yep. Can you see the screen?
That's excellent.
Can you see?
Yep. Yes.
And it's full screen.
Yes, that's fantastic.
Yes, perfect.
Okay, thanks.
I'm glad.
Thanks.
So hello everyone. I'm Cassius Manuel from the Max Perutz Labs, well, concretely from CIVIT, and I will present the work I've been doing with my supervisor, Anfo Hesselab, and it's about the matrix exponential.
Okay, so my name is Joshua Stevenson. I'm a PhD student here at UTAS. And I've been looking at this modelling circular genome rearrangements. And so I've drawn these two circles here that are supposed to represent circular genomes. And so bacteria, for example, often have single chromosomes, and those chromosomes are circular, so rather than just being a string of DNA, they connect back up onto themselves. And so given two genomes that look like this, we want to ask what is the evolutionary distance between these two things in terms of genome rearrangement events. So rather than thinking about point mutations, we're thinking about evolution as large sections of the genome breaking off and reconnecting in some other place. So I've got these two genomes here, and there's numbers all over them. And these blue numbers are supposed to represent the positions of these. I have Do Not Disturb on, but I'm still getting notifications, so don't read any personal messages.
I think you have turned it off. It didn't look like it was on. It's not.
Have I?
Flight mode's on, but Do Not Disturb is not.
Can you turn your Wi-Fi off?
Turn your Wi-Fi off. That's a good idea.
Yes, I think I can.
There you go. Cool.
This is Do Not Disturb, right? This bell.
No, it's the little moon.
Is it?
Yeah.
I don't know how to use this thing. So what was I saying? The blue numbers are supposed to represent the positions. So, so these are physical kind of objects in space. And by writing the blue numbers down, I've decided that I'm going to fix them in a specific position. And then the black numbers are the labels of the regions. And these regions could be genes or segments of a number of genes. And so in these two different genomes, we've got these same 5 regions showing up, but they're a bit shuffled. So they're pretty similar. It's just that in the one on the right, we have region 4 and region 1 have swapped. And so in this case, to go from this genome to the other genome, we just have to swap regions 1 and 4, or equivalently swap the regions in positions 4 and 3. And hopefully, if I have time, I'll explain why it's useful to separate the idea of positions and regions like this. Right, so almost everywhere in the literature, these genomes and the rearrangements are represented with permutations. So, for example, I can write this genome on the left as a map from regions to positions. And it's a permutation because I'm using the same labels for regions as I am for positions. So I can write the regions along the top. And then just write the position that each region is in. So region 1 is in position 4, region 2 is in position 2, 3 is in 1, 4 is in 3, and 5 is in 5. And so permutations are always used to represent these things, but sometimes in a slightly different way. So sometimes people will write these as maps from positions to regions, and maybe even regions to regions where each region maps to the one that follows it in the genome. And I should mention that I could have written this in a number of different ways, because if I change my position labels, or equivalently, if I just kind of spin the genome around, then that's going to change the permutation that I write down. But it'll still represent the same physical genome. And so we can also represent the rearrangement as a permutation, but this time we want to think of it as a map from positions to positions. And so for this particular one, we're swapping the things in positions 4 and 3. So positions go on the top. And the thing in position 4 goes to 3, and the thing in 3 goes to 4, and everything else stays the same. And so if we call this alpha and this thing sigma, then if we multiply them alpha sigma, we're going to get another map from regions to positions, and it will represent this genome here, where we've swapped regions 1 and 4. Right. So the goal is to think about what paths of rearrangements I can apply to go from one genome to the other one. And so people have thought about just the minimum number of swaps of 2 adjacent regions that you need. But obviously there are lots of different paths, even just to go between these two, where you apply rearrangements and then they undo them. Right, so yeah, so these things are always represented with permutations, but it's not always, people don't always think about the fact that we're dealing with the symmetric group in particular. And that's helpful in a number of ways. For example, I mentioned that I could have used different labelings and I would have different permutations to represent the same thing. And we can think about that kind of rotational and reflective symmetry by thinking about the dihedral group. Dn, D5 in this case. And so any permutation in the dihedral group, if I apply it to sigma, I'll get another permutation that represents this same genome, just moved around in some way. And so we can think about the set of cosets if we take the symmetric group. And we want Dn sigma. And so these cosets are really what correspond to the genomes themselves. Right, okay. So, but one of the things I've been thinking about is what happens when we want to add more information into this. So I said that we can go from this one on the left to the one on the right by swapping regions 1 and 4. In this case, it's equivalent to kind of, when I say swap regions 1 and 4, you can do that by kind of cutting the genome up in these 3 places and moving them and reattaching them. But also you could just cut it in 2 places and then kind of flip it and reattach it. And these are the same thing in this case because we're not keeping track of the orientation of the regions. So these regions are strings of DNA. So if we kind of flip it over, then the DNA will be running in the opposite order. So what we want to do is have some orientation on these. So for example, we can have just draw some arrows. Like that. And then And then so the permutation, we're going to use positive or negative numbers to let us know whether we're going clockwise or anti-clockwise for the particular region. So in our map from regions to positions, we have the same regions along the top. But this time region 1 is in, so I'll write the positions down again. Region 1 is in position 4, but it's going backwards. So we're going to write a minus sign on the 4. And region 2 is in position 3. It's going backwards. And region 4 is in position 2. 5 is going forwards. And 3 is forwards. But so this isn't a permutation anymore because it's a map from, numbers 1 through n to plus and minus those numbers. So we want to extend this so it's a permutation again. And the way we do that is we just say, well, I need to figure out where to map these things to. And we can just map them to each one of the, I don't know what that line's about. Each one of these we can map it to the negative version of whatever the positive one mapped to. So 1 maps to -4, so we can just map -1 to 4. And we can map -2 to 3, and -3 to -1, and -4 to 2. And so what we're doing is we're saying, if this is sigma, we're saying sigma of -I. We're going to set that to be minus sigma I. And so this is what's usually done, but again, people don't often mention the subgroup that you get from this. So this is a permutation in S2n, where the 2n letters are ±1 to ±5. And if you take the permutations that satisfy this, then you get the hyperoctahedral group, Hn. So it's just everything in S2n such that sigma minus I is minus sigma I. And so this symmetry thing I was talking about before, so we get a copy of, lots of copies of the dihedral group in Hn, and one of them in particular works to describe the symmetry of the oriented circular genomes. How much time have I got?
You're just about out, I think.
Oh, right, okay.
We've got a 30-minute one.
I can't remember.
I think you started about 1 minute late, so maybe you're due to finish at...
No, he's should have another 15 minutes.
Oh, hang on, sorry, you're right. Yeah, so you're fine. Yeah, yeah. Cool. Beg your pardon, I misread the time. Chairman's mistake, sorry, carry on.
Well, I'll just talk about whatever I have time to talk about, I guess. So what's the order of this group? So it's pretty easy to see because we started with a permutation in Sn, and there are n factorial of those. And then we just went through everything in the image and decided whether we wanted it to be a positive or a negative. And so there's 2 to n different decisions there. And then we extended it uniquely to be an S2n. So that's the order of the hyperoctahedral group. And I thought it was cool that this looks sort of familiar, maybe. If you know that the number of rooted binary trees is 2n factorial on 2n factorial. And so here is the this is the order of S2n, and this is the order of Hn. And you can come up with a bijection from rooted binary trees to these cosets in S2n quotient Hn. And this isn't a group, unfortunately, because the hyperoctahedral group isn't normal in S2n. But I think the bijection is quite cool, and it's described here in this paper. And they use it to, along with the representation theory of S2n, to prove some results related to random walks on binary trees. So I'm going to talk about this because I think it's cool. So if we just draw a tree and label it in a certain way, so we're going to write down the labels we're going to use for the vertices. So we're going to use 1 and -1, 2, -2, 3, -3. And the order that we're going to use these in matters. So we're going to start by labeling the children, the leaves, 1 and -1, 2 and -2. And then we're going to start with the ones we labelled first and label the parent with 3. And then this one's the -3. And there's the root there. And then so we can identify this with a matching, or so matching is a kind of graph theoretic term, but we're going to write it down as a permutation in cycle notation. And we're just going to pair up the siblings. So 1 and -1 get paired up, and 2 and -2 get paired up, and 3 and -3 get paired up. And so this is just a permutation that's saying 1 gets mapped to -1 and vice versa, 2 gets mapped to -2 and vice versa, etc. And the permutations in S2n, where n is, I should mention, by the way, this is rooted binary trees on n+1 leaves. The permutations in S2n that fix this permutation are the ones in the hyperoctahedral group. So if you think of a permutation in the hyperoctahedral group, whatever it does to 1, well, by conjugation, I should say. So if we let this thing be then sigma, gamma, sigma inverse is gamma again, whenever sigma is in Hn. And the reason is, well, when we apply a permutation by conjugation like this, it's going to map each of these things to whatever it maps them to. So you can think that the hyperoctahedral group is whatever it does to 1 here, it's going to do the minus version of that to whatever it does to -1. So you can see that it's just going to shuffle around these pairs, and so it's going to satisfy this. And if we did another tree, oh no, I don't know what this line is either. It's gone. Oh, that's back. If we did another tree, so that. And then do the labeling. So we're going to have -1 and 1, 2, -2, 3, -3. And we get a different matching. Then we can write this in terms of this one up here, because this is just that one, but we're going to map 3 to -2. Like that. I think that's right. Yeah. And so the permutations that fix this under conjugation are going to be the ones that are in here. And so we can map the tree to the matching, and then we get the permutation that we need to apply to get back to this balanced tree one. And it's fixed by this copy of HN, and then we just map this to the coset that coset in S2N. And all these maps are bijections, and so that's where you get the order of this set, the size of this set being equal to the number of binary trees. I'll do it. Cool. So yeah, I just wanted to mention that because I think it's cool, and I'll just, with the last 5 minutes, talk about what I've been thinking about recently. So I mentioned that this swapping these two regions is different from inverting this segment. And when we're thinking about these distances, we want to consider some rearrangements that we think make sense. So maybe we want to consider all these inversions of two adjacent regions, or maybe all inversions in general. And I kind of think about it in terms of where the genome gets cut into pieces. And so I was trying to work out whether there was some algebraic way of describing where one of these permutations makes a cut on the genome. And so you can write down the number of cuts that a rearrangement makes. So if we have a rearrangement alpha, we have this special permutation C. I'll just do n is 5 for now. And this represents the order that we want things to go in. So the kind of identity genome is going to have the regions going in a clockwise order. And if they're negative, that means it's been flipped over and we want them to be going anti-clockwise. So this permutation kind of describes that information. And then we can write the number of cuts, or the set of cuts for a given permutation, as the positions I and Ci, where if we go to the next position and then apply the rearrangement, we want that to be the same as if we applied the rearrangement and then advanced the position. So it's going to be a cut if that's not the case. And so then you can say that when the size of this set of cuts is 2, then we're thinking about an inversion like this one. And when it's 3, then we're we're kind of shuffling things around. And it's quite nice. I think that there's a lack of kind of these slightly more algebraic descriptions of some of these concepts in the literature, and I want to kind of put things into these terms because I think they're easier to work with and easier to prove results with. That's it, I think.
Thanks so much, Josh. And nicely on time after all that. I'm terribly sorry about the halfway interruption. Any questions we have for Josh? No one else from outside? However many there are, I'm not sure how many there are. Barbara.
So having, like, being able to express things in this way, will it allow it to be sort of slotted into some of the stuff that Venter's sort of presented on previously, where you kind of think about sort of words of these sort of operations and then like being able to use the sort of representation theory approach, or there's still sort of quite a bit to be done to get it to that point? Or?
Yeah, I'm not really sure yet, but I kind of, it at least helps me to think about it. So
yeah.
We'll see.
Any others? Well, I do have a question. You've got this nifty association with binary trees, at least as far as I understood. Does that suggest any kind of evolutionary thing of how the rearrangement got to where it is, subject to, you know, it's all a coset? Does it tell you in what order the rearrangement? I mean, a simpler binary tree is sort of, I don't know. You know what I'm trying to say in terms of how the genome rearrangement got to where it is.
Yeah,
Does that make sense?
I think so. Not that I can't. There's no relationship that I can tell beyond just the bijection. But it's sort of interesting that this kind of the hyperoctahedral group as a kind of algebraic structure shows up in a bunch of different places.
Yeah. Interesting. Other questions? Final comments? Or are you saving it all for the discussion?
We'll say it's lovely to see a whiteboard talk at Philomania. Well done.
Yes. And we'll move right along then. Thanks very much, Josh.
How's my hand? Good? Yeah. Okay, it's sort of a generic name. I probably should put my name on it. And I've lost my notes, I've lost what time it is, everything, but I know the next speaker is Julia Shaw, one of the postgraduates from our group, talking about phylosymmetric algebras. Thanks, Julia. Tell us who you are anyway, for the benefit of everyone.
I'm Julia, I'm a PhD student here still. I think this is my 5th or 6th time presenting as a PhD student at UTAS, because I've gone part-time. Seems like a lot of time. So I wanted to talk about phylosymmetric algebras, which is some work I've been doing with Michael Hendrickson. My supervisors left me to my own devices for a few months, and this is sort of what fell out of their benign neglect. Okay, something about Philomania, just I was kind of excited. Like, first I was like, I'm not sure about an online conference, but then I heard Joe Felsenstein was coming, and I was like, oh my God. I think I could speak for a lot of people in the room to say that, oh, we do feel a bit like that. A bit scary though. So an executive summary, which is something I didn't actually know what it was until yesterday. Thank you, Conrad. So from another project I did in my PhD, there's this way of generating rate matrices, which I'll go into in a minute. It turns out they had some really cool mathematical properties. So we investigated some of these, and thanks to Michael Hendrickson, it's now linked to graph theory. So I was like, yeah, that's pretty cool. Okay, so we remember a rate matrix. Can look like that. We have 0 column sums because the Tasmanian phylogenetics standard. That's what a rate matrix can look like. And then usually we put little asterisks in the diagonal entries to save space. And sometimes I have free parameters, so they can look a bit like this. So this would be a whole set of rate matrices because alpha, beta, and gamma are all any real numbers. So it's like a whole set. So, and we all remember what phylogenetic trees look like. This is just one I pulled out of my head. There's some things on it. We have the nodes, the internal nodes represent speciation events. Yeah, can you see them?
Orange-bellied parrot.
I think I wanted birds that started with certain letters. I think that's why I did that. So yeah, the little nodes here represent speciation events. So like this was the point where speciation happened. But we can put different things on the leaves. So here I've done something quite dangerous. I've put amino acids on the leaves. And we're assuming there are only 5 because a 20 taxa tree doesn't look particularly approachable on a slide. So what we've done, but then the question is, like, are we suggesting that amino acids evolved? No, not quite. I'll go into that in a minute. So single letter abbreviations are easier to look at. I think that's why I put albatross, eagle, whatever. Okay, so the idea is, this is Peter Wills's ideas from University of Auckland in New Zealand. There's references to that. So the idea is we're looking at an organism's ability to pick out the correct amino acid. So way back in time, it's like, all right, the DNA says that we want to find alanine, so we want to find A. And it goes to find alanine, but it's going to pick one of these 5. It's not going to do a very good job. It's going to pick one of these 5, which is not pretty rubbish. So it's not going to translate genes particularly accurately. They're pretty much random. But then, the mechanism's got a bit better. And then we say, all right, well, now we can distinguish these 2 groups. So it's like, okay, so now if the DNA says we need alanine, it's going to pick alanine, cysteine, or glutamic acid, I think. One of those 3. So it's a little bit better, but it's still going to do a pretty rubbish job. And yeah, the idea is that we have sort of a progressive, we get better at picking out the correct amino acid. And yeah, with the study we did on Peter Wills, we kind of used this idea to sort of test some hypotheses. It's very cool. I think it was cool because I did the analysis. Okay, so now what we're going to do, we're going to assign rates to the nodes. All right, so we're getting even more dangerous here. And we define the rate of change between 2 taxa to be the rate associated to the most recent common ancestor. So if we have our tree like this, and we want to find the rate of change between A and E, we're going to get gamma. Rate of change between D and F, we're going to get delta. C and F, we're going to get alpha. So that's sort of how it works. And then from that, we can build a rate matrix. So it looks like that. Okay. And yeah, so that's what I did for stuff with Peter Wills. And then afterwards, I was like, these are kind of cool. Let's look at the algebraic properties of these matrices because, for every different tree topology, there's a different one of these matrix sets, which is kind of cool. Super joke. Okay, so we generate rate matrix sets. And what we found was that a rate matrix set like this actually forms an abelian matrix algebra. And by that I mean a matrix vector space that is closed under matrix multiplication and it's commuting as well, which is really cool. So yeah, if we multiply 2 matrices that look like that together, we'll get another one that looks like that. And I think because they're symmetric and it's closed, therefore it must commute, I think. But yeah, it does compute. It does commute. So next thing we looked at is if we had a matrix set and then we set alpha to equal to gamma, do we actually still have a matrix algebra? So if we change those 2 gammas there to alpha, if we multiply 2 matrices together like that, will it look like this? No. In the general case, no, it isn't, but sometimes it is. So if we multiply two of these matrices together, what we will find is, sure, all these little alphas there will be the same, but they won't be equal to the numbers that come up there, generally. So it will be contained in a matrix algebra, but it's not a matrix algebra in its own right because it loses some information. Okay, and then we sort of looked at different sorts of trees, and here are some. So the little green ones, it's like, well, if we make that rate and that rate equal, then the corresponding matrix sets, or the phylosymmetric algebra we generate, is an algebra. But these cases, they are not. So you can sort of see, we're sort of looking at those, like, well, what's going on, what's going on? And then I came to Philomania 2019, and Michael Hendrickson had some very interesting ideas about what to do with it, so we started having a look at it. And he said, well, if you get a rate metric set like this, and we find the basis element that corresponds to coefficient alpha, and by that I mean L alpha being this, so every time we see an alpha, we put a 1, and then we just make sure the 0 column sum is adhered to. Then this is actually the Laplacian. Now, I knew nothing about graph theory, so it was very handy to have someone that knew about graph theory who could tell me these things. So this graph there, and we can have a look at the tree as well, just so we can sort of see. So the rate's alpha, and we can sort of see that D and F are all connected to C, E, and A, and they're the only edges. So everything on this side connects to everything on this side. So that's a graph theory thing, which is kind of cool, and I'll just sort of have a look at the other graphs. So here, if we look for beta, and we see that A and E are on this side, and we've got C on that side, so C is connecting to E and A. And then there's that one, which is pretty simple, and that one, which is pretty simple as well. So that was kind of cool. And then we thought, well, we want to sort of, well, Jeremy sort of came up with this idea. Actually, I probably should have put him in the beginning. So if we have, like, if we sort of take the L alphas and L betas and L gammas and L deltas, like, how do we multiply them together? And we sort of found the general form of those. And I won't give you the exact form, but if we have alpha and beta such that alpha sits higher in the tree but is above beta, we'll find that if we multiply them together, we're going to get some scalar multiple of L beta, which is kind of cool. So we do know exactly what that X would be, but there's only, I didn't think people would, well, if I was watching this talk, I probably wouldn't absorb that much information at once. So just things to do with the tree. If you want more details, it's all in the paper. It was published last week.
This morning. There was an announcement this morning from the journal announcing the paper.
Oh, because it was on their website last week. Okay. Oh, this morning.
Congratulations.
And then if we square a matrix, we're going to get a matrix that is some scalar multiple of L alpha plus scalar multiples of things that are below alpha. So if we were to look at this one, if I were to square L alpha, I'm going to get scalar multiples of L delta, L beta, and L gamma as well. So there'll be a whole linear combination of everything, and if we wanted to square L beta, we would get scalar multiples of L beta and L gamma, and we know what the coefficients would be. We have worked that out. We actually worked them out using linear algebra and graph theory, but then I thought it was cool having two proofs of the same thing using completely different approaches, but the journal didn't think so. So they thought this is redundant information, and so we kicked out linear algebra. That's okay. And then we wanted, okay, so using these sort of rules of multiplication, we wanted to figure out what are the conditions on a tree such that the resulting matrix set is an algebra in its own right. And I copy and pasted this out of the paper because I was like, oh yeah, I don't need to write that out again. Then I realised that it's like incredibly difficult to read without spending 2 slides on terminology. So I've just sort of done the quick version, which is probably a bit inaccurate, but you sort of get the gist of it. So we got, if you have 2 rates on a tree, and we make them equal, say alpha and beta, when will we still get a phylosymmetric algebra? So when will the corresponding matrix set form a matrix algebra? So either if alpha is directly above or below beta, like on the tree, or they are both directly below some other node and have the same number of leaf descendants. So that is the only time that it can happen. So that was kind of cool that we showed that. And I suppose what I think these things could be cool for, in particular, would be amino acid substitution models, because there are hardly any parameterized amino acid substitution models. Like amino acid substitution models, what do you think? PAM, BLOSSOM, LG, and they've all got like preset numbers in them. They're empirical, so there actually aren't many parameterized ones, but this method could actually give us some parameterized ones with actually a pretty low number of parameters. All right, so thank you for listening, and here are the references.
Thanks very much, Julia. Any questions? Well, I had a question. I hope you paid your copyright to Jackie Chan. That's all. Otherwise, I'm going to beat you up. Jeremy, I think you have a question.
Yeah, I have a comment actually. So what you're trying to do with that work was find there's some consistency conditions for when you have these relations on the parameters. And this is exactly what Mohammed had in his talk with his group-based models and the embedding problem. He had some consistency condition on a labeling function, which is doing the same job of making some parameters equal. So it's a different context, but it'd be worth looking at if there was some insight into comparing the two. So you can take that as a comment, if you like.
I did have a serious question. I mean, these...
That was serious.
Quite serious. Finding these abelian matrix algebras and so on, I mean, that must be a classic problem. And who invented this tree method? Was it Peter Wills, or was it someone else?
I think Peter Wills sort of came up with the idea of having the rate of change being the most recent common ancestor, but I'm not sure if he considered the mathematical consequences of that.
It's just amazing. It's just incredible.
They're really fun little set, actually.
Yeah.
Fun linear algebra.
Yeah. Anyway, we've already. Sorry. Yeah. Well, you don't need to see me.
They can't see you.
Yeah, but that doesn't matter. We've already thanked Julia twice. We've clapped Julia twice. So I'm not sure if we should do it again, but perhaps we should do it again anyway. And thank the other speakers for the session. And that's the finish of the scheduled sessions. And we now, that's right. And we now have 15 minutes. So we have a time to think about or ask questions from other things that you may have thought of during the session, or indeed we've got the two pre-recorded talks. So I'm assuming that you've all been, well, I was last night, instead of going to the pub where everyone else was, I was assiduously listening to the talks of Jeremy and Benta. So I assume you've all been doing that this morning or something. Well,
can we get Jeremy and Benta to give their quick statement?
As I say, in the meantime, you may have some other questions that came up from the previous discussion, but let's ask Jeremy and Benta to give a 2-minute summary of what their talks were, so we're all on the same page.
So should I come on?
Jeremy? Yeah.
Do you want to go first?
Yeah. So I'm just giving Peter a hard time not being in the camera. So where do I actually look?
Yeah,
So
you're on.
where do I look? So I'm looking into the camera. It's there, isn't there? Yeah. Okay, so my talk was looking at, it's related to the embedding problem, and you're looking at when you've got a Markov model, and it's a continuous time Markov model, and it's your model is some collection of rate matrices defined some way, like, so think of GTR, or think of the Kimura model, or think of its symmetric rate matrices, or just some sub-model, and you're asking the question, if I work with that sub-model, when do my Markov matrices look like my rate matrices? And we saw that discussed in Mohammed's talk, where he was talking about how this is sometimes the case and sometimes not. So I'm just asking, not in the context of the embedding problem, but just asking generally, when does this happen? And the surprising answer to this is there is a unified way of thinking about why this happens. So you may know that for the time reversible models, you definitely have this situation. So an easy example is if you have symmetric rate matrices, you certainly get symmetric Markov matrices out of that. So you have this nice correspondence. But there are other examples like like the doubly stochastic model. Okay, so the doubly stochastic model also has this property. And so I wanted some kind of general characterization of exactly what it is about your rate matrices that's causing your Markov matrices to have the same structure. And the answer to that is that up to some technical statements, which I attempted to do in the talk, the answer to that is that you want your rate matrices to form what's called a Jordan algebra. And so it's interesting because what it's saying is, I think I have to run at the board, is instead of doing matrix multiplication of your two rate matrices, you should multiply them one way, then multiply them the other way, right? So you say, okay, I'm doing a new operation which I call star, and I just add the two different ways I can do the product. And you're asking the question, if Q1 and Q2 are coming from some model you're thinking about, is this also in the model as well? Okay, so you're asking the question, is that product also in the model? And that, when the answer to that is yes, and the technical thing, the model is linearly parameterized, when the answer to that is yes, then if it's an if and only if your model has this property that your rate matrices and your Markov matrices look precisely the same. Okay, so that's the characterization, and it unifies a bunch of examples. So that's the point. The other thing to say about it is what's going on with this plus. Well, what if I had a minus? And you might know this business that we talk about with the Lie Markov models and multiplicative closure is exactly the dual to this, where you say, well, instead of a plus, you could have a minus with some operation here. And so the amazing thing is this question about the Markov matrices being the same as the rate matrices, there's a duality with the multiplicative closure question, and they're both resolved in this context, whether you take a plus or a minus. So it's quite a nice little story, and that's what my talk was about.
Thanks, Jeremy. Do we discuss, what's the plan? Do we discuss Jeremy now and Benta in a minute? Okay. Any questions for Jeremy? Well, I had a really deep philosophical question. I mean, if Élie Cartan was thinking about groups back in 1903 or something, and didn't think about matrix exponentials or something, but knew about Poisson processes like we saw with your talk, could you reconstruct group theory just by a stochastic approach? Because you're really getting to in the end, you're talking about a group of.
Yeah, I guess that's a good question. So like a lot of this stuff is like that kind of interaction between the stochastic probability world and the algebra world. Yeah. We're kind of trying to bring those two things together. And that's where I said, there are some technical aspects that you have to worry about and be careful about how you're doing these things, because you're really talking about convex sets, whereas in the algebra sense, you don't usually have any of that.
Yeah.
But I think that's right. I mean, if you had, I guess you'd have to get to Markov, talking about Markov chains, and then this idea of uniformization of the Markov chain. And you could start to ask this kind of algebraic question, and then maybe be led down a path that made you start to invent a theory of algebra. Yeah. So I think that's plausible, but that's historically not what happened. So matrix groups and the theory of algebra goes back to the what is it, the early 19th century. Yeah. We had to wait to the 20th century for the theory of probability.
It's a funny thing that some exceptional Lie groups, they're not actually realised as matrix groups, but people still managed to talk about the exponential map. So it's rather strange.
Yeah, that's the other thing I should say about this work. It's kind of, the thing I love about it, it's so elementary. It's just matrices. It's just elementary stuff, right? And we're sort of finding these nice little elementary things that aren't really discussed in the sort of pure maths literature so much. It's really nice how phylogenetic just throws up these really simple but fundamental objects and structures. Yeah. Okay.
Okay, well, that's the end of the sermon. Does anyone actually have any other questions for Jeremy? We'll move on to, thanks for it, Jeremy. We'll move on to Benjamin.
Okay, so I guess we've heard quite a little bit today already in the session about Markov models, and group-based models have been mentioned. And so what I wanted to say in my talk, and I think I did not say the exact words, but what I wanted to say was, okay, a lot of people think that group-based models are nice, group-based Markov models are nice. Are all nice models group-based? And the answer is no. So there are quite a few models that I use, like the equal input model, the Felsenstein 81 being a particular case of that are not group-based. So a couple of years ago, Jeremy and Michael Woodhams found out that this particular model, the equal input model, is an example of a semi-group based model. And what we've added in the last little while is that we can characterise all irreducible semi-group based Markov models in a quite simple way. So the equal input model has this idea of constant rows, the way I like to write it. Some people might think they're constant columns. So you get the idea, something's constant. And this comes from something called the left zero semigroup. So the thing that you're multiplying by on the left is what you end up with, no matter what you're multiplying it by. And so anything that's an irreducible semigroup-based Markov model comes from one of these, a semigroup that is isomorphic to a left zero semigroup just crossed with a group. And that's it. So we've got a bit more work to do to investigate the properties of these, but having that characterization is nice. It means we know what they all look like. If we've got one that looks like this, if we've got something like this, you know, we can create examples. That took me 30 minutes to explain in my talk. I'm not quite sure how I did that, but I didn't have time to re-record it. So you might want to watch it on double speed if you haven't watched it yet.
And I listened to all of it, so that's very good. At least I'm one person. No, there were several people who'd seen it, I think. So very good. Well, mini clap. Questions for Venter then?
Yeah, I had a question. Right at the end of your talk, you showed like the list of the number of irreducible semigroup models for each order. I was just sort of wondering about that sequence of the numbers. If you sort of, it's like a known sequence, if there's any other patterns apart from the prime thing that you've noticed, or like if it's on the encyclopedia of integer sequences or something like that?
No, so I put it into the encyclopedia of integer sequences and it wasn't there, but these things are known as left groups. So they're a really well-known thing in semigroup theory. And people have looked at left groups, and so I would have thought they would have just, said how many left groups are there of small orders, so up to a certain order, but no, it's not in there. Really odd.
Have you added it?
No, not yet, but we haven't written the paper yet either.
Yeah.
And I should mention this is joint work. It began as an honours project with Nicholas Popenick.
Well, speaking of semigroups, I mean, you've only got to talk to some of our colleagues that we can think of from our department or elsewhere. And there are so many definitions and categories and, well, I shouldn't say categories, but so, think of some definition of a semigroup and ask whether it's relevant to your thing. So one thing is this mysterious inverse semigroup, which is commonly associated with putting a star on the symbol. So, I mean, I guess that could be a transpose or something like that, but does anything like that pop up in helping to characterise the whole story from that point of view?
Yet to be done.
Well, we'll wait till the next presentation then. Yeah, I don't know.
So I actually have a question.
Show your face, Marmon, is it?
Yeah. So for the group-based model, we have this. So if at the end of the day, you want to like compute this joint probability distribution of like, observe nucleotide at the leaves, right? Using this model. For the group-based model, you have this discrete Fourier transform that could like simplify the parameterization. Like for this semi-group-based model, do you have like, analogous way to like simplify the joint distribution probabilities?
Well, I haven't thought about that at all, but I can't see how you could get a Fourier transform without having inverses. I haven't looked into it deeply, but my first thought is, how would you do that? But I don't know if people have looked at it at all, Fourier transforms on semigroup. There's certainly been, a lot of people have studied a lot of stuff about semigroups, and, we're really at the beginning of our journey. But yeah, that's one of the things to look at. Yeah, Jeremy has a comment.
Add to that comment. So certainly you won't get a diagonalization, but because we know the structure, so if the group G there is abelian, and we know the structure of the left semigroup so well, there should be some kind of block diagonal form that we can use, which should be fairly easy to characterize, and we just need to do it. And as Vincent said, it should be known in the literature to the semigroup theorists. Yeah. But the point is, it's going to be a block diagonal form is the best you can get.
Yeah, I mean, I discovered recently that, how you have group algebras, there are also semigroup algebras, and in certain types of semigroups, these are, nicely reducible and so on. So, yeah, there's definitely will be something we can do. We're just not sure how far.
Well, Michael, quick one.
Just a quick one. So, I mean, with these very interesting algebras and groups of rate models, do you see that some of them might be, I guess, identifiable from observed data? Is there some way that we might be able to go, okay, it actually fits one of those, this different kind, this fits a Lie algebra based, or this fits a Jordan algebra based, or a semigroup based model better? So it's a general question, I think, for all those involved.
Yeah, I mean, so these are certainly contained in the Lie algebras, and they're they contain all of the group-based models. So I guess for me it's a question of how easily can you describe them and how easily can you find them, and then what does that give you? What extra properties do you get? Like Mohammed asked, does that mean we can more easily do the computations? I guess the first step is to classify and describe and then find out. Yeah, so I don't know. Jeremy, do you have a comment?
I think the comment would be that when you're working in a class of models which has certain structure, then it may throw up alternative methods.
Yeah.
Like so the Hadamard conjugation and this sort of thing. So, I mean, that's not really answering your question, but that's just another way to think about it.
I think it's a very hard question to answer. But, thank you for that.
On that note, for further work, that's probably a good place to stop. I'd like to congratulate all the speakers and presenters and the way it's all gone well, and my personal acknowledgement of the hard work of the organisers as well. I know we've got another session in, half an hour, is that right? Yeah.
Yes.
Yep.
I think it is, should be at 15:15, is that right? Yeah, it begins at 10:15, so in almost exactly just under 30 minutes.
So I'd also like to commend people for using very various types of technology, like the whiteboard presentation, Jeremy's thing last night, and Venter's low-tech presentation. But I'd just like to say that you could go lower. I mean, I look forward to next time somebody coming on with a slate and a piece of lead and doing it, or maybe we could, it's pretty easy to draw trees in sand, right? So you need a stick and some sand, and then you could give a talk with even lower technology. So that's a challenge for next time as well. And with that, we'll break for morning tea. Okay.